As early human civilizations expanded their trade networks and built larger cities, the raw volume of transactions scaled up alongside them. Eventually, the sheer number of daily calculations outpaced the human brain's natural capacity to process and store them accurately. To solve this, we began to externalize our memory. The abacus, appearing around 3000 BC, utilized physical beads to hold data outside the mind. This allowed for reliable addition and subtraction through physical movement rather than mental strain. To reach the next level of complexity, human society required an autonomous solution, a machine that could execute a long sequence of logic without a human guiding every single step. In the 19th century, Charles Babbage proposed a radical theoretical design, the analytical engine. Babbage split the architecture into two distinct zones, a store for holding data and a mill for processing. Ada Lovelace expanded on this by creating the first algorithm, logical instructions telling the machine exactly how to manipulate the stored data. By combining memory, a processor, and a programmable set of instructions, Babbage and Lovelace reached the conceptual pivot point, where the calculator became a computer. In the 1940s, electricity allowed us to build these conceptual machines. They were powerful, but required immense physical space and high-voltage power to function. ENIAC is the definitive example of this first generation. It could calculate far faster than any human, but as this image shows, it required an entire room and a team of operators just to function. The hardware bottleneck was the vacuum tube. These components were enormous, fragile, and generated intense heat, making it physically impossible to scale this technology down to a personal size. The leap to the second generation came with solid transistors. They performed the same function as vacuum tubes, but were significantly smaller, cooler, and more reliable. Through the 1970s, engineers packed thousands of these transistors onto integrated circuits, eventually creating the microprocessor, an entire computer's processing logic condensed onto a single chip. This miniaturization allowed companies like Apple and Microsoft to democratize the technology, moving the power of a massive mainframe onto personal desks and into the hands of individuals. This decades-long engineering effort to shrink the physical hardware was the only way to release the true power of general-purpose computing to the public. Today, microprocessors are ubiquitous. They have become the portable, invisible infrastructure that powers everything from our laptops to our global networks. We are now entering the fifth generation of computing, defined by the rise of artificial intelligence and machine learning. The paradigm has shifted again. Instead of humans writing every rigid step-by-step instruction, modern systems are refining their own logic by identifying patterns in massive datasets. These systems now process information and recognize complex relationships at a speed and scale impossible to achieve through manual human programming. In the 5,000 years between the abacus and modern AI, our relationship with technology has fundamentally shifted. We have moved from physical tools that merely added numbers to digital systems that now identify patterns and generate logic, extending our ability to navigate the complexities of our world.